Hello, and welcome to the fourth and final video in this video series. Ahead of me, in front of me, I have the code that we've been working on for the past 3 videos. So if you haven't checked those out yet, make sure to check them out and see how we got this entire code. Again, we have these 5 functions we created. We've set out different situations and saw how they go over time. We got this phase lag and decibel graphs, and then we also have a total of 3 graphs. This one and this last one with our output or input. So I'm just going to head and run all just to make sure everything is working and accurate again. Then for this video, we will be doing something a little different. We'll be still using the same code. However, now we will be generating at first 50 points for the step response for this whole situation of these 2 tanks for 15 seconds, and then we will add a normally distributed error around each value with a standard deviation of 0.02. Then we will fit that data using a FOPTD model, and then minimizing the sum square error between the model and the data. And then we'll be doing a few more things with the PI and the controller gain, which we'll find out later on. So with that being said, let's go ahead and jump right in. So like we said, we want to create the step response of this whole process. So go up here, create a new code. And then very simple, what I'm going to do is create a function that multiplies these 2 out, which is called down here. So I'm actually just going ahead and copy and paste this. So Control X, and I'm going to call it TF underscore process, right? Because it's our process. Command V, and then TF process for a process. Right, and then we want to figure out the step function. So TF process dot step. Click Shift Enter on these 2. We see that we are given 2 different arrays, right? First one, of course, is for our time, and then this is our H2 derivations with respect to that time, right? So we can go ahead, this ran well. We can go ahead and create a function for what we wanted, or not a function, but spread this out. So I'm gonna call this T expected, right? And then it's simply going to be a linearly spaced, right? And we said from 0 to 15, and we want 50 total points. So we want this when t is equal to t expected, right? We see that we get exactly 50 points from 0 to 15 for both our time and our H2 derivations. So now we can go ahead and plot this out. I'm just going to go ahead and grab this. I don't think we need, no. So I'm going to go ahead and fig equals make subplots. So we can make this out, and then we're going to change our x and y values, of course. Our x value is going to be our t expected, and then our y, we haven't made that yet. We want to unpack these values, right? So for the first one, we have a value for our time, and then for our H2, let's do H2 expected, right? And that's what our y is going to be. We don't need these columns or rows. We don't need a name, however, we do need a specific mode. As we are plotting data, we want to make sure we have markers. So mode is equal to markers. I believe it's no capital, yeah. Then we don't need to update this, and we should be good to just go ahead and Shift Enter. Okay, there we have it. There is our graph. Very simple. You can see it starts at 0, and then it seems like it's cutting off at about 2, right? So if you remember what we said we want to do, we wanted to create a standard deviation of 0.02. So let's go ahead and do that. What I'm going to do is create a random number generator. So I'm going to call it RNG for random number generator. And I believe it's simply, we're using numpy still. And it's random state, if I'm not mistaken. Dump state, yeah. And then we're just going to put a bunch of numbers that we could use. I'm just going to keep it simple and use 1, 2, and 3. Right? And then we can go ahead and recall that down here for H2 expected. And what we want to do is update it. I believe it's mp dot, or no. I believe we have to recall this RNG dot normal, I believe we have to do, and then we have to give it what it has to locate. So very similar to our values that we gave, so equals our H2 expected, and then we have to give its deviation. I think we just put 0.02. That's what we want, right? 0.02. No, that's not right. Or I think our size must be 0.02. I think that's what we need to do. Check that out. No. Shouldn't be size. I think it's, let's see. I think it's scale. There we go. That's okay. Sorry, I just recalled the wrong thing. Scale 0.02 for error. There we go. So now you can see that it still follows it, but every once in a while we get some random values just to give us that standard deviation of 0.02. So now that we've gone ahead and gotten this down, our next step is that we want to fit the data using a FOPTD model by minimizing the sum square error between the model and the actual data. So one thing we got to take care in account is this expression that helps us kind of better understand this equation, or this expression that we will be putting in, and that is k times 1 minus e, or e as exponential, to the power of negative t for time over our tau. And what we need to take account, we're putting a new variable so that we can get rid of all these values under 0, and that is theta. So we're going to add this theta, that is this distance roughly about here, but we'll use that mathematically to get the accurate number. And so the new expression becomes k times 1 minus exponential to the power of negative t expected, which is our value that we got here, minus our theta, which will be down here, all over tau, obviously. So with that being said, let's go ahead and make that. So I'm not sure to make it under. Yeah, I guess I'll do it here. So define FOPTD, and then we're having a vector, of course, that we're gonna have to unpack. We're gonna need k, sorry. We're gonna need tau, and we're gonna need theta. I think I'm gonna put theta second. And that is all equal to our vector. Now, like I said, we want this expression. So we said k times, we have 1 minus the exponential. We're going to use our Jack's numpy, which we've been using throughout. So our JNP, exponential for exp for exponential. And then, like I said, we're going to have negative our t, our t expected, minus our theta. That divided by our tau, right? Should be good. K times our 1 minus. Okay, I think that looks good. And then we're going to want to return some squared error between the difference. But first we need an actual guess. So I'm going to call simply v guess for our values. And then for k, our theta and tau. So it looks like it starts at 0, obviously, and ends off about 2. The slope looks about 0.5 divided by 2. So I'm going to go ahead and say we'll give 1 for k, give our theta a 4 just to make sure it's within that, and then our tau, we'll just give it 2 because that looks like where it's ended up. And then we have to create a function, some squared error, and of course our vector. And then what we were going to want to return is the difference between our v-guess and I'm missing something. We want to return the difference between these two. So do np.sum, I believe, and then we want the square root. So the difference, we want h2 expected, I believe, what we had, and FOPTD. That's for the v, that's for the both, and then squared. Then I actually forgot something. This is not what we want to return. This is simply our y. We want to return what we said we wanted to do is minimalize this and make that a 0. So I'm going to return it. I think it's a numpy. We do numpy when or where, and we just say when our t is smaller than our theta. So when our t expected is smaller than theta, then we want our x to be 0 and our y to be y. Right? So this should be good. And then now what we want to do is minimize this, right? So np dot minimize or I think we might not need it even numpy. Minimize, yeah. We want to minimize this SSE, right? Or we want to minimize the difference. I'm not sure. Let's see what this gives us. Oh, well, that's the point over v-guess, right? So that we could minimize that. So we want SSE. I think we need the v and our v-guess. Let's see what that gives us. Maybe we just don't need this. Okay, there we go. Finally it worked. Sorry about that. So here are our values that we care about, our x values. We were given 2.053, negative 0.424, and then 3.418. I think these numbers might be wrong. Well, we can graph them out and see what happens. So I'm actually going to call this variable so that we can use it later. Let's call it result. And then we should be able to go ahead and plot this, right? Alright, I think that looks good. So if we go ahead, pull this, make subplots, we want to add scatter, and then we want to add one more of these. Our T remains the same, our H and our mode will be different. So our Y, now we want this FOPTD, but with our result. So I believe we do FOPTD with result.x so that we pull out those x values. Or actually, I can make this a little bit easier. So I think that x, let's see. No, that only gives us the first. Okay, so if we're going to do that, make this result. Result should have those variables. We don't need to do this here. And then mode is actually going to be our line. And we should be good, I believe, right? Let's see what we get. And no, there's an issue. I think it might just be as simple as an S for our lines. Yeah, there we go. Always. Okay. And as you can see, here is our line that, as accurately as possible, traces out the value. As you can see, this looks like to be our theta, about 0.918. So much more than our initial guess for. And you can see it looks about fairly well plotted out for our graph. Sweet. So now that we've gone ahead and done that, we can go ahead now and determine the optimal ITAE controller gain and reset time for a PI controller. And thankfully, we have a table given to us already. I'll put it up here so we can try and do both at one time. As you can see, I'll put it in the middle for now. We are going to be using two equations that are down here for our y, and where's the other equation? And this other equation for our expression, and we will be using these values for this set point, this for p and this for I. So with that being said, let's go ahead and put these values in our code. Just gonna go ahead and put it in here. Okay, so now that we've gone ahead and set that up, let's go ahead and put our values. So for our, start off with our y. Right. And we know that it's A for PI 0.586. And that is being multiplied by theta divided by tau. Make it theta divided by tau. And this is all to the power of b. And our b in this scenario is negative 0.916, so negative 0.916. And then I think I have to unpack these values as well. So our, what do we have? Our k, it's getting a little confusing. This, where do we have it? K, theta, and tau. K, theta, and tau should just be our result, I believe. Yes. Okay. And then, so this should be good for our y, 0.586 multiplied by theta divided by tau. Okay. And y is k times kc. So I believe this whole thing would be divided by our k, right? So all of this divided by k. I think that should be okay. And then we can do our value for our tau I, right? So our tau I is simply equal to, so if we were to multiply by tau I, divide that by theta. So theta, and then divided by a lot of things. It's going to be divided by A plus this whole right-hand side. So our A, we have 1.03 plus B, and our B is going to be negative 0.165. 0.165, and then that multiplied by our theta divided by tau, and that should be all we need from this table. Make sure this looks good. We can go ahead and get rid of this plus and just make it minus. Right. I think that should be good. So now if we go ahead and print our KC and our tau I values, we see these are the variables that we get for this unique situation. And I believe that might be all we need to do for our third situation. And we can go ahead and get started for the closed loop response. I think there might be an issue with here. I don't want them to have pulled this information in. Okay, well, there's only one way to figure out if these values are right. Make tau O equal to 0. I think that's all we need to do. Yeah, let's go ahead and plot this out, right? See what it looks like. What do we need? We're gonna need, I think our forward expression, or Q1, QH. Q1 to QH2, did we change that? Okay, yeah, our TF process. Where's our TF process? I'm just gonna go ahead and I guess run everything and see how that looks. Go ahead and run everything. Go all the way to the bottom. So yeah, that shouldn't be TF forward. So a bit too many graphs and I think too big also. It's getting a little confusing. All 400? Okay. Phase. Multiply forward. So KC and tau I. I think I'm just gonna grab this information and just try to plot that out, I guess. So, I mean, our H2 so what did we each do? We determined our Kc and tau I for our PI. Now we want to simulate the closed loop response of the two tangent series, not the FOPTD, with a PI controller to set change, step change. Where's our step function? Oh, I think I might have had to put it before this. Let's see if that does it. Let's delete this. Try to put it up here, I guess. No, because it has to be after a result. Maybe I need to put it down there. Oh no, I have to put it under. Of course. So let me could honestly delete this as well. So let's see. I think I might have switched these values up for this entire thing. I think it should be tau and then theta. Let's see. Possibly in our Vegas. Not quite sure why this could be. Alright, well, what is our Kc value and our tau I? It's still 0.96. Okay, so I've changed something. Not quite sure what I am doing wrong, but let's find that out together, right? I'm really embarrassed to say this, but I think I know this is wrong. This should be our tau, not our theta. That's why I don't click Shift Enter or Tab as fast. So our tau I looks better, but I think our Kc is still an issue. Let's see what our graphs look like. Okay, there we go. So yeah, it was literally a simple factor of just switching out this theta to our tau. I don't know how that slipped past me. I apologize, but we should be all good now. As you can see, this step function looks very, very smooth, as it looks like it has reached steady state at just under 20 seconds. It seems to be constant at 1 throughout, and it reaches it 0.99999 recurring at about 46, 47, 50 seconds. At 50 seconds, it gets fully 1, but very small, minimal, as you can see. So this seems very stable. Now for the last part, we want to perform the Bode frequency that we did from our previous video and kind of see how it reacts with that. So let's go ahead and look at this. I think let's might as well just run it again. And as we can see, we can go over the phase diagram or phase margin and the difference between the two. So as you can see, it's changed off a little bit, and it seems as if it doesn't even reach 180 degrees. Yeah, in fact, 175 is the most. And it seems like it reaches a negative number relatively quick as well. So that's pretty good. So with that being said, let's go ahead and check out the phase margin, right? So we go ahead and see. First of all, it doesn't hit 180, so we know that that means it's stable in that manner. And then we got to look for when it reaches over 0. Looks at about 0.57 is the point where it reaches 0. 0.57. We go ahead and look 0.57 on this graph. It's just about in the middle. Looks like a much higher temperature than the 180 or 160. So what do we say, 0.57? Yeah, 0.57. We see that we get about 120, 123 degrees. And again, if we add that to 180 degrees, we end up with a positive value, which shows that this is currently in a steady state, or this situation is currently in a steady state, and this unique circumstances are all checked off. So with that being said, thank you for watching this final video, and I hope you guys found this series very helpful and amusing. Thank you. Bye-bye.